Okay, so I forgot to press this recording. Hopefully this will work right now.
Okay. So let A be the sum of the degrees of the odd vertices. Okay, and B be the sum of the degrees of the even vertices. Yes? So it means that I check my list, some of those numbers are odd. I add them together, I call it A. Yes? And in my list, some of these numbers are even. I add all of them and give it a name B. Is that clear? Yes? So then can you tell me what can I write instead of this, instead of in terms of capital A and capital P? I just want you to understand the notation.
A plus B.
A plus B, yes? So I'm telling you that in my list, some of these numbers are odd. I add all the odd numbers and give it a name to the sum, A. And I do the same thing for even vertices, and I add them and I give it a name. So definitely this becomes A plus B is equal to 2Q. Yes? But now, what can you tell me about the evenness or oddness? It's called parity. When you say parity, it means evenness or oddness. So what is the parity of A? What's the parity of B? Can we say something about it? Yes?
They both either have to be even or odd.
Yes? Okay, that's correct. But now we can say something definite about B. Is B an odd number or an even number?
Even number.
B is definitely even, yes? I have a bunch of even numbers, I am adding them. So it doesn't matter if you are adding odd number of even numbers or even number of even numbers, yes? For example, if I add 2 plus 4, it becomes 6. I have 2 even numbers, I add them, the result is 6. But I have, for example, 3 even numbers. It doesn't matter. For example, 2, 4, and 6. If I add them, it becomes again an even number. So it is clear that if I have a bunch of even numbers, because all of them can be written as a multiple of 2, yes, I can factor a 2 out. So it is clear that if I add even numbers together, it's always an even number. Is that clear? So this becomes even. And now let me move B to the right. So A becomes equal to 2Q minus B. 2Q is even, B is also even. So what can I conclude about A? A is even. Yes? So we know that A plus B is 2Q by this reasoning that every summand in B is an even number, so the sum is also an even number. I move this B to the right, it becomes 2Q minus B. I know 2Q is even, it's a multiple of 2, B is even, so the subtraction of them, so the difference between them is also an even number, yes? But what is the meaning, what is the consequence? If I ask you to go and look inside A is a bunch of numbers added together, but what type of numbers? Odd numbers, yes? But I have a bunch of odd numbers added and then I know the sum is even. This cannot happen unless the number of summands is even. Is that understandable? Yes or no?
Yes.
Yeah? Okay. So it means that this means that the number of summands which means the number of odd vertices is even. And that is what I wanted to show. Yes? So it is very simple. This is coming from my theorem. I just open it up. I say to myself, some of them are odd. I collect them and add them together and give the sum a name A. Some of them are even. I collect them together and add them and give it a name B. Here, B is definitely an even number because I am adding a bunch of even numbers. It doesn't matter how many of them are there. The B is definitely even. And then I move B to the right. This is even, this is even. I conclude that A is even. But A is a sum of a bunch of odd numbers. and I know the sum is even. This cannot happen unless the number of summands itself is even. Because if I have odd number of odd numbers and I am adding them, the result will become an odd number at the end. Yes? Is that clear? Okay, so that's the reason that in any simple or multi-graph, so it is, you see these, I really like these kind of things. The arguments are so simple, but they are very, very general. And for example, this is a very nice problem. When I saw it for the first time, I was really excited. So because this problem, let me read it for you. Is it possible to draw 15 line segments? We don't know about the direction of these line segments. We don't know about the length of these long segments. But so it means that this is a very wild problem, yes, because I have infinitely many degrees of freedom. You can imagine any type of 15 line segments in any direction in a space with any length that you want. But we are asking a very generic question. Is it possible somehow come up with this drawing that we draw 15 line segments such that each of them intersects exactly 3 other line segments? This doesn't seem to be a graph theory problem, but you see that this is a very nice problem. Do you have any idea? You see, this problem seems very hard, yes? Because I have a lot of degrees of freedom. How can I even imagine 15 line segments in a space, in any way, with different lengths? You want to say something quite astonishing, that is it possible or not? If it is possible, you need to have an argument. If you say no, you might have an argument for that one as well. And it is somehow related to what I said here. But you need to find the connection. That finding the connection is interesting. Yeah, don't splash the door. So how can we connect this problem into graph theory in the first place so that we can use this? Yes, please?
Could we think of the problem instead of lines, it's vertices, and then we try to create a simple graph where each of the 15 vertices has a degree of 3.
Yeah, you're very, very close, yes. So you are saying that, so you are representing each line with a vertex, yes? So that's completely correct. And then, what are the lines in your, how do you connect the lines? If you say that, that's everything is complete.
The lines are the intersections.
No? So how? So you said that, yes. So what Alex is saying is this: you have 15 lines, yes. But for each line, so you have 15 lines. Let me choose a vertex called L1. This is of course not the real thing. The real thing is a line segment. I am just representing it by 1 point, yes. So I am saying that L1 represents the first line segment, call it L1, yes? And then I go, for example, assume that someone has drawn this in this situation. We want to show that, no, this is not possible. This is the idea. This is not possible. We want to say it's not possible. So someone assume that has drawn this. I take the picture of that person. What I do, I put a node L1 for the first line that I see in the picture. I put a line node L2 for the second line, and I do the same thing up to L50, yes? And then I look at the picture. If L1 and L2 in that picture are intersecting, I draw a line between them. If they are not intersecting, I do not draw a line. So do you understand? Assume that someone has drawn this and gave it to me. I look at that picture and I try to draw a graph for myself based on the picture that I have in my hand. So I represent each one of those line segments with a point, and I call it L1, L2 up to L15, and then I take the picture. I check L1, with any other lines. If L1 is connected to L2, I draw a line. If it is not intersecting, I do not draw a line. And then I go L1 with L3. If L1 and L3 are intersecting, I draw a line between them. If no, I do not draw a line. Assume that I spend a lot of time and then check every situation. At the end of the day, what do I have here? I will have a simple graph. Is that clear? It's completely clear that I will have a simple graph. But what would be, if I ask you what is the degree of L1 in this graph, what do you think it will represent? For example, if you see that there are some edges coming out from here and then one here and nothing here. So when you say the degree of L1 is 2, what do you understand in the picture? You understand that L1 is intersecting exactly 2 of them. Yes? So the degree here means the number of intersections that L1 make with other lines. Is that understandable? So now the question is that, is it possible to draw 15 line segments such that each of them intersects exactly 3 others? So it means that, is it possible so that the degree of each one of these vertices be exactly 3? Why not? Because we have how many vertices? 15, which is odd. If all of them are odd as well, so it means that I have a graph with 15 vertices, all of them 3 of degree 3, which is not possible because we just showed that the number of odd vertices should be an even number. If such a thing happens, it means that this will give rise to a simple graph so that the number of odd vertices is odd, which is in contradiction with this theorem. So it is not possible. So I think this is a very nice problem. It's a very indirect problem related to the graph, yes? So it is completely clear, don't use your energy, you will never ever be able to draw such a graph, such a picture. Is that understandable? The argument is understandable? Okay. Okay, now let us go to the new topic here. So there are many words, I don't know the Swedish ones, also, they are also in the book, but I want to introduce you some terminology, okay? So there are things that we need to know. So these expressions, we need to know what is the meaning of a walk, a closed walk. So let me write walk, trail, and path. Yes. So these are the words I want you to know. And then there are something called closed walk, a closed trail, we will call it circuit, and closed path, we will call it cycle. So these 6 words you need to know. I don't know the Swedish translation for them, but you can see them in the book. Okay, so what do I mean by a walk? By a walk means you start one point on the graph and traverse the graph at some point and stop. Yes? And then closed walk, it is clear. Yes? Start from any point, do walking around the graph and come back to the same point. So technically this is, but if you want to make it very mathematically very precise, you need to define. So a walk on a graph is a alternating sequence of vertices and edges. Yes? For example, let me draw a picture here for you. So assume that I have this graph. Yeah, let me do it exactly here, not to waste time. So here we have A, B, C, D, E, and I also have this, and then I have this one, F. So assume that this is your graph. Of course, in this case, this is a simple graph. I do not have multi-edges, I do not have loops. So that's a simple graph. So if I start from any point and then go through the graph and reach to any other point, that is called a walk. In a walk, I don't care about to be careful at all. I can just go randomly any way that I like. Yes? For example, let me write it here. for example, if I start from A, I go to B, yes? But here, in principle, I need to mention through which edge. But here, because the graph is simple, I do not have more than one edge connecting in A and B. When I write A to B, then it is clear that I have to use this only edge, yes? If this is a multi-graph, so I will talk about that. So let me make it a multi-graph. Okay, so let me write it here, and then I have to give names, E1 and E2. So then this is ambiguous. When I say A to B, it's ambiguous because it's not clear am I going from A to B through edge E1 or through edge E2. Okay? So in that case, I would emphasize it on this arrow. Okay? For example, I would say this. I choose E2 from going A to B, and then from B to D, and then, for example, then I go to E, and then I go to C, then I go to B, then I go to C, then I go to F. For example, so let us see what is happening here. I started from A, I have chosen a point, and then I went to B through E2, so from here, and then from B, I went to D, and from D, I went to E, from E, I went to C, and from C, I returned back to B, and from B, I went to C again, and then I went to F. So that's a walk. Yes? So you don't need to be careful at all. You start from a point, you go randomly, you go through the graph. It doesn't matter if you are repeating edges or if you are repeating vertices. For example, here it's clear that I am repeating this vertex here and there. I am repeating, for example, this vertex C here and there. Did I repeat any edges? Yes, for example, do you remember at some point I use this edge, then I return back, I use the edge again. Yes? So there are no limitations. I start from one point, I traverse the graph and reach to the other point. So that is called a walk. And the number of edges that I am using is called the length of the walk. So what is the length of this graph? Of this walk? 1, 2, 3, 4, 5, 6, and 7. So that is called the length of this walk. Yes? And of course, if I start from a point and return back to the same point, that is called a closed walk. Yeah? So for example, if I want to represent a closed walk, for example, what can I do? I can go from A to B. I can go from B to C. I can go from C to D and go from D to A. So that's also a walk. But it's a closed walk because you see the initial point and the final point are the same. And if I ask you what is the length of this walk, closed walk, you would say 1, 2, 3, 4 because I have used 4. But of course here I have to be careful. Let me write E1 on top this time. So this time I used E1 to go there. Is that clear? So these are terminologies that you need to know. So what is the meaning of trail? A trail is a walk that you are not allowed to repeat any edges. That's called a trail. So for example, it was not a trail here, yes, because I repeated one edge at least once. So you are not allowed to repeat any edges. So trail. And no repetition of edge, an edge is not allowed. Repetition of an edge is not allowed. Okay? And then, of course, there are many names. If the trail is closed, you call it circuit. Yeah, so circuit is a closed trail. Yes? So circuit means closed trail. Yes? And of course you can guess what is path. Yes? What is a path? Yes?
You go through all those?
No. That's a different story. But what is path? Here, in a walk, you are allowed to repeat vertices and edges if you want to. In trail, you're allowed to repeat vertices but not edges. Yes? Here in the path, you're not allowed to repeat any vertices. Of course, if you are not allowed to repeat any vertices, automatically you're not allowed to repeat any edges. Yes? Because if you repeat an edge, you automatically repeat at the vertex. Yes? So when we say a path, so repetition of a vertex is not allowed. Yes? So this is the path, and this is the trail. Okay? And this, if I ask you what is cycle, you would say closed path. But one thing that I want to mention here, you might be a little bit of confusion. When I say closed path, automatically the first vertex and the last vertex are the same. But when I am telling you you are not allowed to repeat any vertex, in the case of a cycle, it's no problem. You can repeat the very first one and the very last one. But you are not allowed to repeat anything in between. Okay? So is that clear? And when we are dealing with a circuit, we assume that our graph has at least one edge. Otherwise, it is not possible to have a circuit. And when we talk about a cycle, we assume that you have at least 3 edges. Okay? So any triangle like this can be considered a cycle. For example, E, D, C, E again. So if I ask you what is the length of this cycle, you would say the length is 3, the number of edges. Okay? So usually this is the case. When we talk about circuit, it's always something that we need to know, that we have at least one edge. And when we are talking about a cycle, when I say that my graph has a cycle, you need to, this is the convention, that you need to remember that I have at least 3 edges. Yes? Otherwise, so for example, this scenario is not considered to be a cycle. If I have A here and B here, assume that I have a multigraph. If I start from A to go to B and B from B to A, so let me just choose this one and this one. I go from A to B through E1 and return from B back to A through E2. This is not considered a cycle by convention, okay? So when you talk about cycles, you need to have at least 3 edges, okay? Yes. Okay, so I don't know, let me just do one example here. Let me draw this graph, and I want to ask you to help me to solve this problem. So we have a graph here, so let me make it a simple graph. Yes, and then I have this situation. A, B, C, D, E, F, and G. Okay, I ask you, you answer me, okay. Part 1, give me a walk from B to D. A walk from B to D that is not a trail. So yeah, you just give it to me and I will write the answer here. I just want to practice to remember these words because the words are very close together. Sometimes we get confused. So this is your simple graph. It's the graph I gave to you. And I ask you, give me a walk from B to D so that it is not a trail. For example, if I go from B to E, E to D, this is definitely a walk from B to, so if I go from B to E, E to D, that is definitely a walk from B to D. But this is also a trail, yes? Because no edge is repeated in that case. But I want you to give me a walk from B to D that is not a trail. If you're yes, son, yeah.
A, B, C, B.
So A to B, B to C,
C to B, and then B to A.
C to B, B to
A.
okay. No, I want to go from B to D, okay?
Oh, from B to okay.
Yes.
B,
B,
A,
B, what?
A,
A,
C,
C,
B,
B,
C,
C,
D.
B. Let me check. So you said that I go from B to A, B to A, yes, and then from A to C, and from C to B, and then from B to C, yes. So you have repeated BC, yes? So that's a walk, that's one possibility, yes? So you started from A, you ended up at B, but you repeated one edge. The edge BC is repeated in this case. Is that clear? So this is a walk which is not a trail. This is just an exercise to practice these terminologies. So number 2. So let me write it. A BD trail, this is sometimes they call it like that. A BD trail means a trail going from B to D. A BD trail that is not a path. A BD trail that is not a path. So it means that by the word trail, you understand that you're not allowed to repeat any edges, but because it is supposed to not to be a path, you have to repeat at least one vertex. This is the meaning, yes? Do you have any idea? Yes, Alex, this time.
B to E,
Yes.
E to F,
Yes.
F to G, G to E, and E to D.
D. Which vertex is repeated?
E.
E. So B to E, E to F, F to G, G to E, E to D. So everyone agrees, yes? So here we started from here, 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 and here. So you see, no edge is repeated, but this vertex is repeated. So even though this is a trail, it's not a path. Yes? Okay, part C, let me just do this one. Part C. A path, a BD path. A BD, yeah, just a path from B to D. That's the question. So what is a path from B to D? Yes?
B to C to D.
B to C to D, yes. It's the simplest one. B to C to D. Yes? So part D, let me just, a closed walk from B to B that is not a circuit. A closed walk from B to B that is not a circuit. So, B closed walk that is not a circuit. Okay, so how should I do this one? Can you help me? So I want to start from B to B. It's a closed walk. It's not a circuit. So it means what? It means that this is a walk, it is closed. When you insist it is not a circuit, it means that you have to repeat at least one edge. Yes?
B to A and then A to B.
So let me write B to A. What?
A to B.
So B to A to B. This is an extreme case. I really a little bit confused here. Is this by convention acceptable as a circuit? In a circuit, we need to have at least one edge. We have it. So, yes, I would say that's correct. So from B to A, and then come back to B, I am repeating an edge. So in principle, if I want to write it, if I call it E1, so it means AE1, BE1, A. Yeah, I think that's correct. Yes, yeah, because according to the definition, this should also be something, a closed walk. It's an alternating sequence of vertices and edges, and then one edge is repeated, E1. Yes, I would accept that. But if I want to give another one, what can I give another example? Yes?
B, E, F, G, E, B.
So B,
E,
E,
F,
F,
G,
G,
E,
E,
B.
B. So which, yes, at least we see that this edge is being repeated, yes? So it's a closed walk, but an edge is repeated. So that's also correct. Let me see if there is other. So let me talk a little bit about part E here. Part E, a circuit from B to B that is not a cycle. So we want to go from B to B. Circuit, it means that edges are not allowed to be repeated. But then I want that it is not a cycle. Anyone else? No? Yes?
From B to E.
From what?
From B to E.
E
To F.
to F
To G.
to G
To E.
to E
To D.
to D
To C.
to C
B.
to B. So you started from here like this, yes? So do you agree that he hasn't repeated any edges, but you also agree that he repeated vertex E? So it is a circuit from B to B, but it is not a cycle. Yes? Is it understandable? And then finally a cycle from B to B. You want to have a cycle from B to B. So let us just write, for example, you can write this, I don't know, square, or you can write a triangle. For example, we can say B to E, E to D, D to C, C to B again. So you can just, so you understand what's the meaning of a cycle, yes? So by the way, for example, do you think this is a cycle or not? So any polygon graph is a cycle, yes? So that's a cycle. So what is the length of the cycle is exactly the number of vertices. But what do you think? Do you think this is also a cycle? Yes, this is, you need to broaden your point of view. People realize immediately that's a cycle because it's close to be a circle or something. But is this also in graph theory a cycle or not? That's also a cycle, yes? Because that is isomorph to that graph, if you remember we talked about this. The way that I drew it, you realize that's also a cycle, even though it doesn't look like a cycle, yes? So for example, what about this one? You see, if I give this in the form of a square, you realize that this is a cycle, but might be you are a little bit confused. By the way, this is not the vertex. I have only 4 vertices and 4 edges. So that's also a cycle of order 4, yes? So it's clear. So now these words, hopefully you remember about these words. Okay, now let me, there are some other terminologies. There are many things in graph theory. There are words. They are not very big things. You need to just know the words. Okay, so let us go to the next step. And that is the notion of a connected and disconnected graph. Connected graph, disconnected graph. So let me write it your definition for you. Okay, so definition. A simple or multi-graph G is said to be connected So what is the meaning of being connected? It means it's one single piece, yes, somehow. So what if you want to define it mathematically, it means that if you start from any point, there is at least a path take you from that point to any other points. If that is the case, we say the graph is connected. So a simple or multi-graph G is said to be connected, so this is the word that you need to know. If there is a path between any two distinct vertices. Of G. If this is not the case, the graph is called disconnect. Okay? So that's also, let me underline these words. So they haven't talked about a walk. By definition, we don't say that a graph is connected if there is a walk between two edges. I think there is a theorem. If you can find a walk from a point to another point, you can also find a path from that point to another point. I think that's a theorem. I don't remember. Is it reasonable? This is why we don't talk about walks, yes? Whenever we can find a walk from a point to another point, we should be able to principle, yeah. I think we can think about this. It's a nice problem itself. So if you have a walk from a point to another point, probably you can eliminate what is not necessary from edge point of view. So because if you are not repeating any edges, that walk is already a path. Yes? But if you are repeating an edge, it means that probably you go back to one of the vertices that you have already had it, so you can just ignore going through that step coming back. You just cut and throw it away. So it might be it's possible to prove it. Yes, I don't think it's hard to prove this one. So this is why it is defined based on a path, not a walk. Yes? So we say that a simple or multi-graph, anyway, that's the definition. A simple or multi-graph G is said to be connected if there is a path between any two distinct vertices of G. If this is not the case, we say the graph is disconnected. By the way, these are very intuitively simple ideas. By just looking at the graph, you immediately understand if the graph is one single piece or more than one pieces, yes? So, for example, I have drawn some pictures here for you. So, let me just draw some graphs for you here. So let us consider this graph G1. This is clear. This is another graph. Let me just draw this one for you. I have done them before, not to waste some time here. Yes, so you see this graph and that graph, it's clear that they are connected graphs, yes? G1 and G2 are connected. Yes, is that clear? So it is clear that if I choose any two vertices, I can find a path connecting the two vertices. But what do you think about this one, for example? It's clear if I draw this one and that one. The whole is one graph. Let me call it G3. This is not connected. Yes?
No, it's disconnected.
Pardon?
G3 is disconnected.
Yeah, it is disconnected. Yes? Because, for example, if I choose this vertex and that vertex, there is no path taking me from this vertex to that vertex. Yes?
Isn't there something more extreme than a path?
What?
A path was the one where you couldn't repeat an edge, right?
No. Any
Oh.
vertex.
Other one.
Yeah, that was trail. Okay? So, for example, what do you think about this graph, for example? So let me call this G4. Is this connected or not? It's also disconnected, yes? Because from here to this one, there is no path. Yes, that's disconnected. But what about this one, do you think? This is also disconnected, yes? It's clear, yes? So G5, G3, G3, G4, G5 are disconnected. Okay. Okay, there is also another terminology. So these, I checked everything. These terminologies are somehow in the book, so this is why I'm just trying to introduce them. Some of them are introduced in the exercises. So there are also two very important ideas here. So we want to introduce an Eulerian circuit. So Eulerian circuit and Eulerian graph. So any circuit in a simple or multigraph that covers all the edges of the graph. Okay, let me emphasize again exactly one. I don't need to emphasize because I have already mentioned circuit exactly once. Of course, if it exists. Is called an Eulerian circuit. Okay, so that's the definition. You see, I don't need to emphasize exactly once, because when I say circuit, by definition of the circuit, I'm not allowed to repeat any edges, but I'm emphasizing it here. Any circuit in a simple or multigraph that, this is important, covers all the edges of the graph. Of course, there is no guarantee that this is always the case. It's possible. If it exists, it's called an Eulerian circuit. A graph containing one single Eulerian circuit is called an Eulerian graph. Yes? A graph that contains at least one Eulerian circuit is called an Eulerian graph. So is that clear? So if I can find a circuit, if I give you a graph, you can start from any point at some point on the graph, at some vertex on the graph, and find a circuit that covers all edges exactly once, if it is possible. That circuit is called the an Eulerian circuit. And if a graph contains at least one Eulerian circuit, it's called an Eulerian graph. Yes, the idea is clear. And the good point is that Euler was able to solve this problem because he was able to prove this theorem as an if and only if theorem. Yes, so it is immediately solved. If you want to see if a given graph is Eulerian or not, you can just count the number of vertices, the degree of each vertex, and immediately you realize it is not, or if it is Eulerian or not. So let me give you an example. Yeah. So for example, let me try to draw the graph first for you here. Yeah, it is a little bit complicated. So here A to B, and then I have C, and then I have a line between these two. Yeah, it seems that I have done it right. Okay, so I give you this graph. By the way, do you find a connection between this Eulerian circuit and the conundrum of Königsberg bridges we started from? If I can find an Eulerian circuit, it means that we are able to draw the graph with one pen stroke without repeating any edges. That's exactly the same problem. Okay, so it is, if you don't know the theorem that Euler has proven, might be it is not that easy task to see if this is Eulerian or not. If you don't know the theorem, there is only one way to justify if it is Eulerian or not. And justifying it is not as harder. Saying that it is, it means that you need to try and find an Eulerian circuit if possible. If you find one Eulerian circuit there, then that's correct. It means that can you draw this picture with one pen stroke without raising your pen and without actually repeating any edges? If that's the case, then it means that this graph is an Eulerian graph. Can you give me a circuit, Eulerian circuit here? So when I check the Euler's theorem, I definitely know that this is definitely Eulerian, because it is very easy to check. Whenever you are done, you can tell me. I don't know, I'm just relying on you. Yes?
I think I have one
Yeah, you should just tell me and we check yours. Yes? Where do you want to start from?
from A
From A. Okay, so let me write A and then
to G
to G
to F
to F
to A again,
to A again,
B,
B,
C,
C,
A,
A,
E,
D,
no E,
E,
D,
D,
C,
C,
E,
E,
G,
G,
D,
D what?
and then A.
And then A. Is that what you said? Yes? Yeah, it's not easy task, yes, but let me check his. What is, am I allowed to repeat vertices? Because there are some vertices repeated. Am I allowed?
Yes.
Yes, because this is it's supposed to be a circuit. Circuit edges are not allowed to be repeated. So let us take the pen. From A to G, hopefully this is correct, I don't need to redo it again. So A to G, so I use that edge. G to F, I use that edge. F to A, I use that edge. And then A to B, I use this one. B to C, yes. C to A, this one. A to E, this one. E to D, this one. D to C, this one, correct. E, that's also correct. G, yes, that's also correct. And D, yes, this one. And then A. Did we use all of them?
Yes.
Yeah, apparently we used all of them, and exactly once, because I have only one dash on each one of them. So you see, it's not an easy task. If the graph is complicated, if you don't know the theorem, there is no guarantee. And then this is very nice. You can follow what Carl said, and you can draw this with one pen stroke without raising your hand. That's exactly the same problem. Do you agree? If I start following what he said to me, I automatically will draw this graph without raising my pen from the board. Yes?
It's also a closed circuit.
Yes. No, circuit is closed by definition.
Ah, yes, yes.
That was trail, if you remember. Trail was the open one. When we say circuit, automatically we mean start from any point, come back to the same point. Yes? Is that understandable? So that's, but you see that this is not easy task to understand. But what Euler showed is very simple. He said that, first of all, of course, this might be a little bit tricky if the graph is so complicated. First of all, the graph should be connected. If the graph is not connected, there is no hope for having a circuit, yes? For having an Eulerian circuit. So, but that is not probably hard to see. This graph, even though a little bit complicated, is connected. But he said that find all the degree of vertices. If all of them are even, you are guaranteed to have such a circuit. You don't need to check it. If you want to see the circuit, you have, of course, to understand how to draw it. But if you want to see if it is possible or not, you don't need to draw first and then conclude that it is possible. So what is the name of this graph? If you want to, you can say that this is an Eulerian graph. Why? Because we were able to find at least one circuit, one Eulerian circuit in the graph. So that is called Eulerian graph. Yes? But now let us calculate the degrees. If I want to write the degree of f, what is this? This is 2, 1, 2, 3, 4, this is 4, 1, 2, 3, 4, 5, 6, this is 6, this is 2, 4, 4, and 4. Agree? And you see that all of them are even. If this happens, you don't need to be worried. Of course, this is a theorem. It is not in the book how to prove it. It is not that hard to prove it. You can prove, for example, it by mathematical induction of the number of vertices and things like that. But don't worry. This is what I want you to know at this level. So if I give you a graph, if I ask you to find an Eulerian circuit, then you have to think and then find this circuit. And then, of course, after finding that circuit, you immediately say that the graph is Eulerian. But if I just ask you if this graph is Eulerian or not, you have two ways. One hard way to find the Eulerian circuit. Of course, if you find it, that's okay. Or you can use the Euler's theorem, yes, to see that if this is possible or not. How should I know that? If all the vertices, all of them, are of even degree, then this is possible. This is Eulerian. If not, if even one single one of them is not even, and then you can conclude that this is not Eulerian. Yes, is that clear? Okay. So now you can see that do you remember what was I don't know. This was the graph Euler drew for this Königsberg conundrum problem, yes? So people were using a lot of energy to go around the bridges. I told you the story a little bit, but we realized that that problem is equivalent to drawing this graph with one pen stroke without repeating any edges and going back to the same point. So it is clear the answer is negative here, yes? Because, for example, what is this? This is the degree is 3. So this means that this is not possible. Even though, yeah, here I have degree 3, 1, 2, 3, 4, 5. Yes, all of them are actually. So they were in a very hard situation actually. Even one of them was not correct. Okay? So you understand that by these simple ideas, we were able to show that don't use your energy, it is not possible to do this. Yes? Is that clear now? Or even this famous one. Do you think that I can draw this with one pen stroke without repeating any? This is a famous, might be you have seen it. Can you draw this with one pen stroke without repeating any edges and going back to the same point where it started? It's clearly not, because all of the degrees are 3. Yes? But there is also another theorem. Sometimes you cannot find an Eulerian circuit, but you can find an Eulerian trail. Okay, so it means that you can start from a point and go through all the edges exactly once, but you are not able to come back to the same point, but still you can draw it. Yes, that is called semi-Eulerian. Let me just say you something about this. Semi-Eulerian graphs are not Eulerian, so it means that you cannot find an Eulerian circuit in them. But they are semi-Eulerian. It means that you can find a trail, not a circuit, that contains all edges exactly once. Yes? So you start from a point, you go through all the edges, but you do not end up in the beginning. You end up at some other point. Yes? So, for example, this one, if I give you this, we can do something like that. And then there is a nice theorem for that as well. So, can I draw this graph? How many vertices are there? 1, 2, 3, 4, 5. This is not a vertex. Can I draw this? Is this graph Eulerian? The degree here is 2, okay. The degree here, 1, 2, 3, 4, okay. 1, 2, 3, 4, okay. But this is 3, this is also 3. So this is not Eulerian. It is not possible to find an Eulerian circuit in that graph. But this, we will see, it is a semi-Eulerian graph. It means that you can find a trail in this graph that passes through all the edges exactly once. So it means at the end of the day, you will be able to draw this graph with one pen stroke without repeating any edges. But the point is that you will not end up at the same point that you started from. Can you draw it, by the way? Let me do my... So if I assume that I want to draw it, yes, without raising my pen from the whiteboard. So I go up here, yes. Let me see if it works. Yeah, it works. Yes, so you see I was able, but do you remember where did I start? I started here, but I was not able to end there. I ended at some other point. And there is a nice theorem. I couldn't start from here and do this. I couldn't start from these two. I have to start with the odd vertex. And there is a nice theorem. If you have exactly 2 odd vertices, this is possible. It is not Eulerian, but it is semi-Eulerian. So you see, here I have 2, degree 2, degree 4, degree 4, degree 3, degree 3. Yes? If I have exactly 2 odd vertices, it is not, of course, Eulerian, but it is semi-Eulerian. It means that I can start at one of the odd vertices and go through all the edges exactly 1, but then I will end up at the other odd vertex. Okay? Yes?
Is that because they're somehow combined into one vertex and counted as one?
I don't understand that argument exactly.
Like, you know, in normal numbers, if we add 2 odd numbers, we get an even number. So if we add 2 odd vertices...
I don't remember exactly the proof, but might be that's an idea there. Yes? Yeah, I don't see it so transparently that you see, yes? Yeah, but anyway, I just want you to know about this as well. That's also a good theorem. So this is a very nice theorem because this is if and only if theorem. This is Eulerian if and only if the degree is connected and the degree of all vertices is an even number. Yes? If this is possible, it's a very simple theorem that by just looking at it you can find it. You can also have this situation. If you have exactly 2 odd vertices, you can draw this picture by one pen stroke without repeating any edges, but the point is that you cannot end up at the same point that you started. And you have to start from one of the odd vertices and you will end up with another odd vertex, yes? Okay, any questions here? Okay, so there is one more thing which is left, and unfortunately it's still not solved. So, and that is a Hamiltonian cycle. Okay, so here we talked about Eulerian circuits, but now there is another terminology that I want you to know, and it is in the book, and that is called Hamiltonian cycle and Hamiltonian graphs. Euler and Hamilton were great mathematicians, yes? So let me just write the definition here. In a simple or multi-graph, let me write if in a simple or multi-graph there exists a cycle, not circuit, a cycle that passes through all vertices Of course, let me emphasize again exactly once. That cycle is called a Hamiltonian cycle. A graph containing a Hamiltonian cycle is called a Hamiltonian graph. Okay? But that is a little bit unfortunate. We do not have any necessary and sufficient condition for a graph to be Hamiltonian. And this is one of the famous problems, that this is exponentially hard problem. So even if you want to use a computer, it's not efficient at all. So if you increase the number of vertices, it doesn't matter how efficient algorithm you are using. I don't know, might be if you want to check a graph with even 20, I don't know, even 20 vertices, it is very, very hard, even you have a very good computer, to see if you have that one. So there are some theorems, there are necessary conditions for Hamiltonian. These are not part of your lessons, of course, but you need to know this Hamiltonian. Understanding a graph is Hamiltonian or not is not as simple as Eulerian one, because for Euler we have a very nice, very simple theorem, but for Hamiltonian, a graph, it is not the case. So you don't need to be worried, of course, but you need for simple graphs, it is not that hard to realize if the graph is Hamiltonian or not. But you know that if you say this is Hamiltonian, is easier because you give me the cycle and I am done. I check your cycle to see if this is true or not. This is one of those problems, by the way. I think the idea behind Bitcoin is also something like this. So the reason generating Bitcoins are extremely hard computationally, but if you have a string of the formula, if you want to check this is a fake one or the real one, it is not hard for computers to check. So Sudoku tables are also like that. If you have a very big Sudoku table, if you want to solve it algorithmically, it's exponentially hard for computers to do that. Okay, and then, but if I give you the final answer, it is easy for computers to check if this answer is correct or not. So this is one of those cases. So even if I give you the cycle, checking the cycle is not hard, yes? But if I want to come up with the cycle myself, if the graph is complicated, it becomes exponentially hard. So this is why you shouldn't expect very, very complicated questions here. So for example, let us consider which one of these do you think is Hamiltonian? So let me give you two graphs, G1. Let me just draw it. Yeah, I have an isosceles triangle here. This is called ABC. And then I have a D here. This is connected to D. And this is E. B is connected. There should be one more. Yes. So for example, do you think this graph is Hamiltonian? How do you answer this question? You need to try to find a cycle that contains all vertices. You don't be careful. You don't even care about covering all edges. What you care is covering all vertices exactly once. It might happen that you are dropping some of the edges. Don't worry about that. In an Eulerian circuit, you will not drop any vertices because you are passing through all edges. Automatically, you will cover all the vertices as well. But here, that's not an obligation. Be careful. You don't need to don't need to cover all the edges, but you need to cover every vertex exactly once and come back to the same point where you start from. But do you think is it Hamiltonian or not?
It's Hamiltonian.
Can you give me the Hamiltonian cycle?
I think it's
A, E,
B,
B,
C. No, you can't do D.
D, yes?
C, A.
C, A. Okay, first of all, I told you that for cycles, this repetition is allowed. Yes, that's by definition. But you're not allowed to repeat any vertex. So what you have written, at least structurally, is correct. But let me check. So you started from A and you went to E. So you see, let me just put a line here. I covered this edge, and then from E to B, you covered that edge. So you covered this one, you covered this one, you covered this one, and then from B to D, you covered this edge and that one. And you go from D to C, you cover this edge and this vertex, and then you return back to A by going from C to A. So you see, for example, you didn't use this edge EC, but that's completely okay. I started from a point, I returned back to the same point without repeating any vertices. And of course, some of the edges were used, some of the edges are not used. But it is clear that I'm not allowed to use any edges more than once, yes? Because if I repeat it, then it means that the vertex is also repeated, yes? So, is that clear? Yes. But I think this exercise in the book is also good. We will learn why this, let me just draw it for you, you can just solve it for yourself later. This is called dodecahedron graph. We will see why this is the name of this graph, but drawing it is a little bit harder. It's completely symmetric. If you see it in the book, you will have a better picture. So this graph has a pentagon outside it. So it's called dodecahedron graph. Okay, so then you have this line from each vertex. It's similar to Peterson, but it's more complicated, yes. And then you have a upside down pentagon here. Yeah, even drawing it is very hard. So then let me see. No, this is not going to work in this way. I have to draw it bigger. So let me draw it bigger. Okay, and then I have 1, 2, 3, 4, 5, yes. And there is a pentagon inside. Yes. And then from each side I have this. Yes. And then from each side I have something like this. So you need to do something like this. Yeah, it is. I couldn't draw it very nice, but it's completely symmetric if you do it. Yeah. So, for example, this would be your duty. Is it Hamiltonian or not? Okay, so I think that's a good exercise. I think it's also in the book. Okay, so you can find a better picture of this graph in the book to see if this is Hamiltonian or not. I told you that if you want to say it is not, it is extremely hard because you need to convince me why this is not Hamiltonian, why it is not possible to find a Hamiltonian cycle for this. But if you want to say it's Hamiltonian, of course this is also time consuming, but you need to convince yourself and find that Hamiltonian cycle. So that's the only thing that you can do at the level of your lesson, okay? Yes, do you have any questions? No? Okay, so we solved this problem starting in the next session. Unfortunately, this Wednesday is also a holiday, so we continue the lesson. And by the way, I have put all the exams on week 22, so you have a lot of exams there, yes? So you have a Math 5 exam and a Math 4 exam on week 22. So this is why I'm just telling you, just try to study them gradually. But of course, I could put it in week 23, but only reason that I didn't put it because if some of you fail or you need to do a retest, there is no other time then, unfortunately. So that's the reason. If you check the schedule on the school stuff, you will see and be informed about the dates. Okay, thank you very much. I stop this video from recording. Hopefully everything works fine here.